Hi everyone and happy Holi. To celebrate this occasion today, we are going to look at something that is very fundamental about how a computer does maths, okay? So let's get on with the video. But guys, before we can get into the meat of the video, I would like to give us a little bit of context, okay? Now we have already seen the four basic arithmetic operation, that is basically addition, subtraction, multiplication and division, okay? The thing is that a computer works with circuitry. Basically, there are a bunch of wires and electrical components that basically perform these various arithmetic operations. I think you may have heard the term called transistor, where they say like the microprocessor in your home PC or laptop has millions and billions of these transistors and they operate to basically do arithmetic operations. Now the thing is that each you have already seen these four operations and how different they are to do. So that means each of these operation would require a certain level of complexity to the circuits and each circuit would be different. So when you are designing a microprocessor or anything like that, an electrical circuit that performs arithmetic operation, it would become quite expensive to manufacture those. So you see, the computer scientists or mathematicians or whatever you want to call them, electrical engineers, they have come up with certain tricks to basically make this manufacturing process cheaper, or to say that they have figured out arithmetic tricks to make sure that you can actually afford the home laptop or home PC that you use. Otherwise, it would only be those will only be affordable for universities and very large corporations, basically. So, guys, let's take the case of multiplication and division. Okay. Now, in case of multiplication, let's see an example. Say 8 times 4. Now you see what this is equivalent to is adding 8 4 times. 8 plus 8 plus 8 plus 8. You see this is basically equivalent and this would give you the result of 32. So you see multiplication is nothing more than a series of additions. Okay. So we have reduced down the process of multiplication where we basically use the add circuit to add a particular number of times. And for the case of division, let's take an example, say 10 divided by 2. This is nothing but equivalent to subtracting 2 as many times as required to get to the number 0, basically. So you see, if you subtract 2 5 times from 10, you will get 0. So that means what we have done is reduce the process of multiplication and division down to the basic addition and subtraction. We have reduced 4 arithmetic operations down to 2. And I know that since we are running this addition and subtraction multiple times, it will take a little bit more time to perform them. But you can get your job done with only two complex circuits rather than four different ones. So guys, with two circuits in our hand, we can say that the job is done, right? But can we push it a little bit further? Okay. Can we say that we can boil down all these four arithmetic operations down to only one specific arithmetic operation? Can that be achievable? Can that be possible to do? I mean, we know that addition and subtraction are two very separate things, right? Actually, you see, computer scientists and mathematicians have actually figured out a way to even do that. You see, all these four operations that you see here can be boiled down to one single arithmetical process, and that is addition. And you see, that is the meat of our video today. Today, we are going to look into ones and twos complement and the process of subtraction using them. So guys, let's remember our objective, okay? We want to transform the process of subtraction into a process of addition, basically. Let's say we are given a subtraction of the form a minus of b. Now we can easily write this down as, say, a plus of minus b, right? You see, we have already done 30% of the work here. we have turned a subtraction into an addition where we are adding a positive number with a negative number basically. So the next step we have to understand is how a computer deals with a negative number. Okay. So let's take a binary number, a negative one, say minus of 101. Okay. And on this side, a negative decimal number, say minus of 329. Okay. Random numbers. So to understand how to deal with negative numbers, let's first study it separately. We separate the minus sign and the magnitude of the number basically. So in order to store 101 in binary, it performs an operation called the complement, or in our scenario the 1's complement, and in the base 10 the 9's complement. Let's see how that is done first. Okay, so minus of 101. Okay, it basically takes the magnitude and subtracts it from all ones. Basically it has to be the same number of digits though. If there are three digits, then there will be three ones basically. So let's perform this subtraction here. It will be 0, this will be 1, and this will be 0. So minus of 101 can be written down as 010, its complement form. Okay, and likewise in the decimal system you simply do this operation by subtracting it from all nines, and again same number of digits. Okay, so from 999 you subtract 329, and that will give you 0, 7 and a 6 basically. Now what is actually happening here is that, say we take a number line here and mark the 0, the negative number will lie somewhere on the left of 0. Say this is 329. What you are doing is we are adding 999 to it and turning it into a positive number basically, 670 here. This is what is actually complementing does actually. Now why do this basically? Well, to say there are two reasons, and the second reason I will tell a little bit later on. But the first reason is that basically, you see, if you are given a scenario where you have to subtract a negative number, say like a minus of minus b, what do you do then? Then you see basically this negative number is already will be stored in its complemented form. Okay, so we again go back to the initial step and turn it into sub addition of a negative number, right? So we have to complement the complement. So if I perform the complement of 010, what do we get? Let's do it. Okay, 111 010, and we perform the subtraction, and that would give back to us 1 0 and 1. You see that we get back to the original number. It is the magnitude of b basically. So you see, it is because of this property, this complement operation is actually done on the magnitude of a number. So you see, these both cases where we have to subtract a positive number and a case where we subtract a negative number is easily handled, because you see the complement will always give a number whose complement will again take us back to the original number itself. Okay, an important thing to observe here, guys, you see, when you have 1 as the digit, when you perform the complement operation, that is 1 minus of 1, it becomes 0. And when you have 0 and you perform the complement operation 1 minus 0, it becomes 1. You see, the digits basically flip in case of the binary number system. So what does that mean? That means, you see, you don't have to go to the convoluted process of subtracting every time. You simply, if you are given a number, say 101, you can find its complement by just flipping the bits 010. See, it is that easy. And again, if you again reflip it back, you will again get back 101. Isn't that neat? And you see, likewise, it is also the same in the decimal system, just it works over a range. You see, when you have 0, it will become 9. When you have 1, it will become 8. 2, it will become 7. And say 3, it will become 6. 4 will become 5. 5 will become 4. 6 will become 3. 7 will become 2. 8 will become 1. And 9 will become 0. You see, as you go down ascending, the other side is descending basically. So this is the relationship here. And that is why in binary system, it is easy to perform the complement operation. It is far more, how will I say it? It is far more easier as well as efficient and less time consuming than even the addition process. You just flip the bits. It's just a NOT operation basically. Now for the sign, okay? So for a number, there are only two possibilities, right? Either it's a positive number or it's a negative number, right? So you see, you have to understand that our human brains can understand symbols. That is why our mathematics have a dedicated symbol for positive and negative, the plus sign and the minus. But a computer does not understand that. For a computer, it is either there is current through a wire or there is no current through a wire. So you have to talk the positivity and the negativity of a number in those terms. And what the computer scientists or mathematicians have decided is that they are going to represent plus as 0 and the negative as 1. And likewise, the positive in 0 and the negative as 9 in the base of 10. Now, obviously, there is a reason for it, but first, let's see how a computer represents a negative number like this. For you see, it stores the first initial bit as a 1 if it is a negative number or 0 if it's a positive. Okay, and then if it is a negative number, it will store its complemented form in the remaining bits. Okay, so in this case it would be 0 1 0. So when a computer looks at this in its memory, in its RAM basically, it knows to treat this at, oh, the first bit is 1, so this will be negative number, and since it is 1, all the remaining bits needs to be complemented, so it would then become 1 0 1. That is how it gets back to the original number. And likewise, in the base of 10, you can represent this negative sign as 9 and then store the complemented form. This would be 670. So you will always know that since it is a 9, it will be a negative number and I have to perform a complement of the remaining digits. So this would become 3, 2 and then 9 to get back to the original number. Now, to understand it why this is chosen, you have to first see this, okay? Any positive number, say 101, this is a positive number, you can put as many zeros as you want in front of it, right? And the value will always remain unaffected. Likewise, for a complemented number, let's say 010, that is supposed to be negative, you can put as many ones in front of it and the value will remain unaffected. Why? Let's complement this. Okay, I have added two more ones in the front of it and let's perform the complement. So this would become 0 0 0. See, the sign bit became 0. All the sign bits became 0. So and the 0 will become 1 0 1. So you see, you get back to the original magnitude of the number. This is the reason why it is chosen to be 0 and 1. And likewise, here in the decimal case, you can put as many nines in front of it as you want to denote the sign. And when you perform the complement of it, you will always get back 0 0 3 2 9. And you have already denoted yourself that if you encounter a 1 in the first digit, you will treat this as a negative number. So this will automatically become 329. See, I know it looks like magic, but there is a logic behind it, all of it. So you see, since you can put as many zeros in front and as many ones in front of the complement, inside a computer, let's say your RAM can store a number, say up to 8 bits. Okay, so what it will do is that when it encounters the numbers, this or say this number, it will store 1 in the first digit, then it will trail a series of 1, 1 1 1 1 1, and then it will store the complement basically 0 1 0. So all 8 bits is represented this way. The first bit is taken to be the sign bit, and the remaining 7 bits are the digits of the number. And the computer will automatically know, oh, so this will be a negative number, and then it will perform the complement on all the remaining bits. So all of the ones will become 0, and then you will get back your original number. So this is minus of 101. See, isn't that neat? So guys, let's look at the subtraction process. Okay, now in subtraction there are two scenarios. Okay, one where the magnitude of a is greater than the magnitude of b, and another where the magnitude of a is less than the magnitude of b. Okay, first we are going to consider this first case. Okay, so in the base of 10, let's say I take two numbers 841 and 329. Okay, I'm going to subtract these two numbers. Let's do it normally first. This would give me 1, so that would be a 2. This would be 3, that would give me a 1, and then this would give me 5. So this is the normal subtraction. This has to be the answer. Okay, so let's see the complement process, how that is done. So 841, the complement of this is 670, and then we perform an addition on this. Okay, so this would be 1, this would be 1 carry of 1, and then a 15. So here we then discard this carry 1, and then we add a 1 to the sum, and that would finally give me 512. This is the process. Okay, and likewise let's see it in action in the binary system. Okay, let's say 1100, and I want to subtract 101 from this. Okay, now this should give me the result of 111. Okay, so let's see the process. So 1100 as it is, then we do the complement of this, so that would be 010, and like I said before, I can put as many 1 in front, so we have to match the number of digits. Okay, so 1 in front, and then we perform the addition. Okay, so this would be 0, this would be a 1, this would be a 1, and this would be a 0 1. Okay, and then we discard this first one, and then we add a 1 to it, and that would give me a final result of, which is the answer that we wanted. See, so guys, now that we have seen the process in action, let's boil it down into steps. Okay, we have a number, we complement it, we perform the addition, and we find the carry and we discard it. Then we add a 1 to the sum, and then finally get the result of it. Okay, so with that out of the way, let's get proving. Okay, let's see how it actually works or why it actually works. Okay, now we can represent this subtraction as 841 plus of minus 329, and that will give me an answer a. I'm assigning it to the variable right now. Okay, so what we are doing in the complement process was that we were adding it 999 to it. Okay, remember the number line that I showed you in the beginning. Okay, so let's write that down. So this equation would then become 329 plus 999, which is equals to a plus 999. Okay, this much is understandable. So now this part now basically becomes 841 plus of 670, right, as shown here in this step. Now see the magic here. Okay, what did this addition come up to? What was the result of that? Was it not 1511? And then that is equivalent to or equal to a plus 999. Okay, now see here, if I change the sides for this 999, what does my equation now become? It becomes 1511 minus of 999, right? I'm not in, I'm not wrong here, right? This is what is actually happening. Okay, now let's add a +1 -1 to this step. Okay, and see what the equation now stands. This will now become 1512 minus of 1000. You see this 1000 here, guys? This is the magic that is happening. This is the reason why you can discard this carry, this one here. You see, there is also another condition to see here. You see, 841 is less than 1000, and so is 329, right? I'm sorry, 670. What you see is that when you add them both, this will always be less than 2 times 1000, right? So you see this carry value here will never exceed 1. This will never go to 2 or more than that. This will always be 1. And it is because of this minus 1000 here and this reasoning here that you can confidently discard this carry in this process or this algorithm basically. And you see this +1 -1 that we did here, it is basically adding this final one here only. And that is how we finally get the answer 512. This is the proof. This is why the complement subtraction process works basically. Now let's represent this proof on the number line. Okay, let's draw number line first. So this is 0. So the first number that we get here is 841, and then we are adding 670 to it, right? Then we are subtracting 1000 from this number, and then we are adding a 1 to it. So you see here, this subtracting 100 process is not a actual subtraction because we are just discarding a carry. So this subtraction, so this process does not count anymore. So in the subtraction total process, we are performing one addition here and one addition here. So this finally becomes that one subtraction is equivalent to two addition. Now, wasn't that our objective from the very beginning, to transform subtraction into an addition? See? So guys, now we are going to look at this scenario where b is greater, okay? So let's take the numbers 841 and I want to subtract 983 from them, okay? Now, this will give me a result of minus 142. So let's see the complement process in action. So 841 remains as it is, and we have to find the complement of this. So that would become 16. We now perform the addition. That would give me 7, 5, and 8. Now see here, no carry was generated. So by rule, we have to perform a complement of this, and that would be 8 would become 1, 5 would become 4, and 7 would become 2, and it would be treated as a negative number. Okay, that's the answer. Now let's look at the same process but in the binary system. Okay, say I want to subtract from 1100 and I want to subtract 1110 from it. Okay, so like before, 1100, then find the complement of this, that would be 0001, perform the addition 1011, and then see for ourselves, no carry was generated, so we need to find the complement of this, that would be 0010. So the final answer is minus 10. So guys, let's get proving this again. Okay, and it is pretty much similar to the previous one. I mean, there is not much difference here. So 841 plus minus of 983, we assign it the value a, the equation, and then we add 999 to both sides, which is the same as the process of complementing, right? So 841 plus minus of 983 plus of 999, That gives me a plus 999. Okay, now this one basically becomes 841 plus of 16, and this is equal to a plus 999. And then finally this is my 857, which is equals to a plus 999. Okay, now we are going to change the sides, and that would give me 857 minus of 999. And then I do one extra step here. I take the minus common and we change the positions, basically 857. Okay, now you see here, subtracting it from 999, isn't it similar to a complementing process? Hmm? That is why you see in the final step, if no carry is generated, we perform the complement process. That is why it is here. And because of this minus sign, it is treated as negative. That is why we are writing down the minus sign in front of it. Now you see, in a computer will not perform this complement step because it is already a negative number and it stores the complement value only. So in a computer, it would simply store it in this step only. It will not store it as minus something like that. It will just take the complement because this is the magnitude for it, the negative number. So it would just add a 1 in front of it and it would just store this basically, or as many ones in front as needed. So guys, with this I end this video. Please write down all your queries in the comment section and please like and subscribe to my channel. With this, I like to say one final thing: to learn, never memorize. And happy Holi guys.